All right. So now we're on chapter 13, image hardening and CICD security. In today's cloud security landscape, one of the most critical issues organizations face is software supply chain attacks. To effectively mitigate these threats in Google Cloud, we need robust approaches to infrastructure security, operational monitoring, and vulnerability remediation. This chapter explores Google's comprehensive approach to compute engine image hardening and DevOps pipeline security. So here's an overview of image management. Google Compute Engine Image is a pre-configured virtual machine template containing an operating system, configurations, and required software for applications or services. Securing these images is fundamental to preventing unauthorized access and malicious exploitation. So there's types of compute engine images. Google Cloud provides two primary image options. Public images. These are produced and maintained by Google, open source groups, or third-party vendors. These are accessible to all Google Cloud projects without additional IAM permissions. While many are free, some premium images may incur costs. Two, custom images. These are organizations' images, accessible only through the project where they were created. They can be shared with other projects by granting appropriate IAM permissions and incur cloud storage fees, but no usage fees in Compute Engine. So what's in a machine image? A machine image captures comprehensive configuration data from a VM instance, including the machine type, the instance metadata, the labels and network tags, preventative maintenance plan, volume mapping, persistent disk information, and UEFI settings, where applicable, right? Machine images don't capture data in memory or local SSD, though local SSD device mapping information is retained. So let's click over here. Go into Compute Engine. While you can customize image compute engine instances using startup scripts to install software and apply security configurations, creating custom images with standardized security baselines is more efficient. These custom images, sometimes called golden images, can be created through three ways. One, manual baking. You can create a custom image from a new instance after manually configuring it. Two, automated baking. You can use tools like HashiCorp Packer to make the image creation process reproducible, auditable, and configurable. Three, importing existing images. Migrating images from existing infrastructure using export, import, or Google Cloud Migrate for a compute engine. So the benefits of custom images are the following. There's faster boot time for applications. There's a more stable environment. There's easier rollback capabilities. There's reduced dependency on external services during startup. And there's consistent software versions across scaled compute instances. We'll open this and the other one. Okay, so encrypting images. All compute engine disks are encrypted by default using Google's encryption keys. Disk images are similarly encrypted during creation for enhanced security. So let's reject that. For enhanced security, you can do the following. One, use your own customer-supplied encryption keys, CSEK, during disk creation. Or two, create encrypted images from disks by providing encryption keys to the image command. So image management pipeline. Creating a secure image management pipeline involves several key procedures. Develop a comprehensive image lifecycle strategy, including golden image promotion, versioning, deprecation, and deletion. Create golden images with automated compliance checks using Chef Inspec. And implement organization policies to limit available compute images in specific projects. So creating images with VM and Packer and with Cloud Build. These are also possible. For automated image creation, you can use HashiCorp Packer with Google Cloud Build. The process is the following. So one, and we're going to go over this a little bit. So we're going to create an instance as a builder. Wait, did I go to the right one? Oh, I don't think I can do that. Well, I can verbally walk you through it. Packer. Here's the Cloud Builder documentation. I'll add this. So anybody who wants this will be able to have this. All right. And I'll add that to the chat. But basically, you want to create a compute engine instance as a builder, create a cloud storage bucket for image storage, create a service account with the necessary permissions, usually around storage, around compute engine, and then around any externals. And then create a Packer template. That's where you need HashiCorp templates, right? Define the builder type, the source image, the zone, and the machine type. Then specify boot commands. That's going to be your Linux commands, and your post-processing steps. Then you install the install the Packer binary, right? So you'll download, install Packer, the command line utility, and let me see if I can go show you the site where this would be at. All right. And then you'd run the Packer build command with appropriate templates and variables. And then you create a build configuration specifying source repos, steps, and triggers, and configure cloud build to handle the image creation process. So this creates a process within your own cloud environment to create images that are outside of Google's direct management and creation. So let's see if we can try and do this. Add this as well into the chat. All right, so you create, let's see, VM instances. Let's see, you go to VM instances, create the instance. Ooh, or maybe, wait. So it would be done here. And you can select the VM you want. But let's try and create this, all right? You create this instance. Well, let's use this one. Let's select this. Actually, we would need the images. Let's create, yeah, so we already got, hold on. I'm a little over the map. All right, let's go to VM instances. Let's create an instance. Let's do this. Golden instance. US Central 1, EC2, or E2. We'll create this. This will just be a low impact instance, right? So then we'll go to images, create an image. Let's choose golden image. All right. Under source, we have disk. Source disk. We'll have the golden image. And then we'll use a Google managed key. We could do multi-regional, we could do family, but we're going to leave this basic. We're going to select create. Oh, because this is already being used. Okay, that's okay. But this is the basic process for this, okay? You can also do this in a CLI with the following command. Sorry, I have to reconnect. Okay, the following command, gcloud compute images create, then the image name, then the source disk name, then the source disk zone, then the image family, and then the description. Okay. All right. So controlling access to images. To maintain security while enabling image sharing across projects, implement the following IAM roles for the image creation project. Okay. I'll add these. You need compute.image user. All right. This is the role for users who need to create instances from these images. You need compute.instance admin. This is for users who need to create instances in the project. And then you need compute.storage admin. This is for users who need to create images and disks. And ensure users have access to the compute.image API to share the images, to use these shared images. Okay. So you can create images across projects as well. If you go back here, click on images. All right. So what you do is click on the image you want to share. Let's say this one, right? Oops. Okay. So you want to click on edit. Now, where is the permission? I'm looking for permissions. Oh, let's see if I can find one that has it. Oh, here we go. No? Oh, here's okay. Here we go. This, I don't have permissions to view. Oh, no permissions. Oh my goodness. Um, Status? No. Let's see. But basically, you'd want to select this, click the permissions, and add the permissions and add the principal using your service account, right? And then you enter that email of the service user or the service account and assign the image user role to it and click save. You can also do it in the CLI, but I'd need to have this all enabled, right? Simplest way, gcloud compute images add -im -policy -binding to the image name, and then the user email, and then the roles compute.image user. Okay. So image lifecycle management. After establishing an image build pipeline, maintaining image currency and preventing the use of outdated images is essential. So there's image families. With image families in Compute Engine, this ensures automation systems always use the latest images without remembering specific image names. Benefits include grouping related images for easier management, referencing family names instead of using specific image versions, and simplified rollback capabilities. As an administrator, you can control image availability by deprecating outdated versions. You do this with the following command. gcloud compute images deprecate Nginx v3 2019 state deprecated. That's an example of what you could do. Okay. So deprecated, excuse me. So deprecated states include, quote, deprecated, which means this is still usable but no longer appears in the image family. Obsolete, which is no longer available for use, though existing links may remain valid. And then deleted. This is completely removed, returning errors when referenced. So you enforce lifecycle policies. You do this to ensure that images are regularly updated with security patches. Key enforcement mechanisms include image deletion policies, setting timeframes for image removal, image retirement policies, defining when images should no longer be used, image deprecation policies, marking images for eventual deletion. So commands like gcloud, let's see, like gcloud compute images deprecate with flags like, let's see, like delete in or delete on or obsolete in or obsolete on help to implement these policies programmatically. Okay. So how do you deprecate or delete an old image? Right. We go back here. So in this area, you would click on the image you wish to deprecate, which would be, let's say, this one, right? And on here, you should be able to click deprecate, which you can see is not highlighted because this is a standard image by Google. But if we had a created image, this is where you would do it. You click save and you'd be okay. And you can enter this command in the CLI to do the same thing. All right. That's gcloud compute images deprecate, image name, and then state deprecated, and replacement with a replacement image. Okay. All right. So how do you delete an image? Well, you go over here, you click on the image, and then you select delete. So you select this image and then select delete up here. But since this is a Google owned image, you can't do that. You can also do this in the CLI with the following command. We'll go back over here. gcloud compute images delete and then the image name. Okay. So let's go into securing a CI/CD pipeline. Continuous integration and continuous delivery. These are CI/CD pipelines. These enable developers to work on smaller code chunks, increasing productivity and efficiency. However, securing these pipelines is critical to protect applications, services, and data. CI/CD security fundamentals. Key security practices include establishing secure configuration guidelines, automating security testing, implementing role-based access controls, monitoring and auditing logs regularly. Common CI/CD security threats include unauthorized access leading to malicious code injection, inadequate testing allowing security threats, missing patches creating exploitable vulnerabilities, poor access controls enabling confidential information threat, misconfigured pipelines exposing private information, data leakage of credentials or tokens, and malware injection disrupting systems. So here's a comprehensive pipeline security approach. One, you need to have your SCA. This is your source composition analysis. This will scan your source code early in development to detect vulnerabilities. You place your SCA at the beginning of the pipeline for early assessment. Then you'll have your SAST testing. This is your static application security testing. This will analyze source code for security vulnerabilities before deployment. Then it'll detect issues like missing input validations, hard-coded credentials, or SQL injections. So let me get a nice image of this for you, excuse me. You can see this. Yeah, that looks nice. All right. Then you'll have CI/CD IAM controls. This will implement strong access control and authentication, use multi-factor authentication or role-based access, and then regularly review and update permissions. All right. Then you'll have secrets management. With this, you avoid hard coding secrets in configuration files or infrastructure as code templates. You store sensitive data in Google Cloud Secret Manager, and you communicate secrets via variables during the CI/CD operations. Then you have container registry scanning. This is where you can scan container images to detect malicious code, verify image integrity before deployment, and then track image changes over time. And then you have container runtime security with secure container environments against unauthorized access. Then you protect the applications from data breaches and denial of service attacks. Ultimately, you have to establish trust in CI/CD, and trust must be explicitly recorded for auditability. As artifacts move through pipeline stages, trust increases with each successful validation. One, you have feature development. This is implicit trust. Two, you have code security tools completion. This is explicit trust. Then you have dev environment acceptance, which is implicit trust. Then you have QA approval, which is explicit trust. Then you have stakeholder acceptance. This is explicit trust. You also have binary authorization. Google's binary authorization service is a security control for container deployment in Google Kubernetes engine. It ensures only trusted containers are used through one, emission controller policies, two, structured policy documents, three, digital attestation for containers. Let's get you an image of this, some source material for this. This is where binary authorization would live. And here's some information about the API. You'll see that in the chat. See, policies can be developed to allow or deny deployment based on attestations with different environments requiring increasingly strict verification. So here's some best practices for CI/CD security. One, use infrastructure as code for resource management. Automate builds and deployments with tools like Jenkins, CircleCI, or Spinnaker. Implement Git for version control. It could be Git, GitHub, Bitbucket. This is where your code lives. Then configure notifications and alerts for pipeline issues, usually through PagerDuty, Slack, email, something along those lines. Then track performance with monitoring tools like Google Cloud's Operations Suite. Then perform frequent testing throughout the pipeline. That was the SAST and DAST. Then you use cloud native tools like Kubernetes and Cloudbill. This is for your application to actually launch. And then adopt containerization for efficient deployment. Then enable automated rollbacks for changes. Then implement centralized authentication with Google Cloud IAM. Also, deploy security monitoring for all CI/CD activities. In addition, follow the principle of least privilege access and make sure you secure configurations using Google Cloud Security Command Center. You also want to monitor and patch vulnerable components. Then you want to regularly back up the CI/CD pipeline. You also need to encrypt data both in motion and at rest. Then you need to utilize containers to isolate pipeline components and set up threat detection systems. And finally, use Google Cloud security offerings. This means Cloud Armor, Security Scanner, and IAM. So Now let's go to shielded VMs. Shielded VMs provide enhanced security against rootkits and bootkits through specialized security features. So let's go over here to the compute engine ish area, the VM instance. Okay, so you would create an instance. Okay, and then let's see. Oops. We'll just leave this. And let's see, custom advanced configurations. Why am I not seeing it? Let's see, storage optimize. Zone. PCSE core count. That's not it. Oh, OS and storage. Sorry. Okay. Jeez Louise, I am missing everything. Okay, so additional disks. Okay, so we're in here. Let's see, boot, data protection, snapshot schedules. That's always good to have a snapshot schedule to define this or back this up. Exclude boot disk. No, we don't want that. Replicate. So networking, tags. These are all useful for firewall rules and policy. Security. There we go. Okay. So you want to set up, enable your shielded VM. All right. Turn on all settings for secure boot. And at this point, you have a confidential VM service, right? So the service adds protection to your data and use by keeping the memory of this encrypted. And then you have shielded VMs, right? So the shielded VMs is trusted UEFI firmware and comes with options for secure boot. We'll open that so you can have this in your selection. Okay. And then when you configure this, all three of these, and you can also do some additional access here to control access through IAM, block SSH, which is always good, and then click create. Okay. You can also do this in the CLI with the following command. Gcloud compute instances create instance name, and then the image name, image project, shielded secure boot, ITY monitoring, integrity monitoring, and in the zone. Okay. So secure boot. Secure boot verifies digital signatures of all boot components, halting the boot process if signature verification fails. Secure boot uses UEFI 2.3.1 firmware to protect certificate repositories. It checks each boot component's signature against approved keys and records verification failures in VM serial console logs. Then you have the Virtual Trusted Platform module, VTPM. Let's go back here and see if we can get in this real quick. Okay. Security. Okay. VTPM. Okay. This is a specialized chip protecting authentication assets, right? This uses Boring SSL library, which is compatible with TCG specification 2.0. It enables measured boot for integrity baseline generation, and then secures secrets through shielding and sealing. Then you have integrity monitoring. This helps evaluate VM security state by using platform configuration registers, PCRs, to store boot information. It compares recent boot measurements against the integrity baseline, and then reports pass-fail outcomes for early and late boot sequences. And then you have IAM authorization, which I believe we showed here, right? So let's add this. I think this might be, there we go. All right. So IAM authorization has shielded VMs use Cloud IAM with specific permissions. And I'll show them here, just so you have a visual reference. Oops. Okay. Compute.instances.shielded update. All right. .instances.update shielded instance config. And then compute.instances.set shielded instance integrity policy. And then compute.instances.get shielded instance identity. These permissions are granted to the compute.instanceadmin.v1 and compute.securityadmin roles, or custom roles as needed. Then you have organizational policy constraints. So you can set constraints. You can set the following. You set the following true. You set the following to true to require all new VMs to be shielded VMs. Then you have confidential computing. So confidential computing, it protects data while being processed through hardware-based trusted execution environments, TEEs. This provides the final piece of end-to-end encryption. This is encryption at rest, which protects stored data, encryption in transit, which protects data in motion, and encryption in use, which protects data during processing. So key features of Google Cloud Confidential Computing. Right. So confidential VMs run on hosts with AMD EPYC processors using AMD Secured Encryption Virtualization, SEV. This provides isolation, so encryption keys generated by AMD Secure Processor remain on chip, inaccessible even to Google. Attestation. VTPM generates launch attestation reports for verification and high performance. There's a minimal impact, maybe 0 to 6% on most applications. Additional services include confidential GKE nodes and dataproc confidential compute. So here's a couple of benefits. There's seamless transition from standard to confidential VMs. There's no application changes required. Hardware-based VM memory encryption also has ephemeral keys, and this completes the end-to-end data protection. So here's a couple of final takeaways. Key concepts include image management fundamentals and the types of compute engine images. How do you create and secure custom images through manual or automated process? How do you implement and robust image management pipelines with tools like Packer and Cloud Build? And controlling image access through IAM permissions. Also look at managing image lifecycles with families and deprecation policies, and then securing CICD pipelines against various threats. Ultimately, you have to realize you're implementing best practices for pipeline security by utilizing shielded VMs for enhanced OS level protection, and you're leveraging confidential computing for data protection during processes. So what you could do after this is create a custom hardened image using Packer with security configurations, right? Then implement an automated image pipeline with Cloud Build. Then configure an image sharing between projects with appropriate IAM roles. Set up image lifecycle policies with deprecation timeframes. Secure a CI/CD pipeline with secret manager integration. Deploy a shielded VM and verify integrity monitoring. And then test the confidential computing with a sensitive workload. So this chapter explored comprehensive approaches to hardening images and securing CI/CD pipelines in Google Cloud. By implementing these security measures, organizations can significantly reduce the risk of supply chain attacks while maintaining operational efficiency in the cloud. Hopefully you see this as a valuable tool, because if you're on the environment and post-test, you'll definitely appreciate it and be valued. Next up will be Chapter 14, Security Command Center. Until then, thank you for listening.